chapter chair, and I've got here with me Julius, vice chair, and I want to introduce our speaker today, Mr. Santiago. So I'll pass it to Julius to introduce Santiago.
Thanks, Anthony. So Santiago is a senior power systems engineer at the planning department of Red Eléctrica de España in Madrid, Spain. He has a Master's in Industrial Electrical Engineering at the University of Las Palmas of Gran Canaria in Spain, and MBA with the University of Barcelona. So Santiago has worked as a power system consultant, SCADA software developer, and markets consultant, and he has a number of contributions to the open source community, most notably GridCal. So Santiago, welcome to this webinar, and we're really excited to hear your talk. So feel free to share your screen, and the floor is yours.
Yes, thank you so much for inviting me.
Thank you, Julius. I've been looking forward to it, Santiago. Yes,
Nice.
All yours. Thank you.
Okay, so welcome everyone, and I'm going to discuss a bit about how we deal with power system analysis today and the current challenges, and what does open source have to say about all this. And I'm going to try to tie all the talk to my experience developing GridCal and what it brings to me as a power systems engineer, and probably to someone else, but not only the program, but open source as a concept. The first slide is the current challenges. We are perfectly aware that we need to decarbonize the whole society, and a big part of it is the electric sector. And this is actually the goals we have here in Europe. This comes from something called the TYNDP, the 10-year Network Development Plan for 2020. And we already see that for 2030, we already have quite ambitious goals of the amount of renewables in the system. So we know that these renewables come at a price, but currently that price is variability. And to deal with variability, the best way we have is to try to incorporate data. For instance, here in the Spanish TSO was the first place in the world that incorporated a control room just for renewables, being aware of the challenges it represents. So what do we have off the shelf to deal with this amount of uncertainty? So we usually have command line software made by us, or we have a legacy, or maybe we hire some university to produce it. And we also usually have commercially available software such as PSC, Dixilent, or ETAP, for instance. And these come in the fashion that you have something like buttons, some schematic or tables, and a text output. And then if we are lucky, we do have also a Python API or some sort of programming language to be able to access and automate the tools. So this year, for my MBA, which I just finished, I did a survey. And the survey was about how are we doing with tools in the sector. And the way I tackled the survey was contacting people individually from my LinkedIn network. And because I wanted to specifically target people from power system planning on operations from TSOs. And once I had a representative sample of people, then I opened the survey to more people, and then we had this share, 60% of TSO, ISO, and DSO from North America, Europe, and Australia as well. Commercial consultants and some people from academic background, and then probably 1 or 2 people from software development. So my first question, or one of the main ones from the survey, was, are the current tools that we use to deal with renewable adequate? So the answers I allowed were yes, fully ready, yes, but we need to adapt them, and no, we are working on it, and then not sure. If you read carefully, you see that the second and the third, so the yellow and red, are exactly the same answer. but from a positive and negative view. And it throws quite an interesting view, and that is, no, we are not ready. The tools are not ready, and we are doing something about it. And everyone is doing something different because everyone feels that the tools are not okay, at least for the challenge. And related to that, I also ask, how would you rate the amount of work needed to collaborate with others? Meaning the amount of work to adapt a model and to register changes. For instance, in the last 2 years, this Spanish planning, it happens every 5 years, so it started in 2019. We did about 3,000 or 4,000 variations, meaning that for every investment, possible investment, we had to do a complete system analysis. And that, as you can imagine, is a massive amount of data produced, and it vastly exceeds the human capabilities. We are not anymore looking at peaks and valleys. We are looking at several years ahead and thousands of investments. So how are the tools dealing with this? So we buy a very expensive tool, so how do we do it? So people in the survey said around 3% said fluid, 14% said extremely time-consuming, and about 30%, I would say, time-consuming, or not ideal. And because of this, I asked also the next question. So how would you rate the in-house tool development effort? So 12% said all commercial, and 10% said all in-house, so probably are those the outliers. I'm guessing the 6% is RT in France, which they have a very strong open source policy. But the rest lies in between. So we usually have some in-house developments. We also have some in-house, let's say, open source or adoptions, but most of that is based on commercially available software. Say that we have a number of programs that run upon PSSC or Dixieland or any other program, and that is the majority. And another question I ask is, would you use open source software analysis tools? And hopefully this came the opposite of what I was expecting, because I was expecting, no, it cannot be trusted, almost everything. But I was proven wrong, hopefully, and 36% said yes, we use them already. Around 40% said yes, but only after internal validation, which is perfectly fair. And around 21% said no, we only use vendor solutions, but that doesn't exclude a vendor that sells you open source, as it happens in the SCADA business. You know, when it's very common that whenever you buy a SCADA system, you ask for the source code. Exactly because of what I'm going to explain during this presentation. So let's jump to 2013, and this is the Netherlands. This is the Clarendal Park. This is where I started. I consider this the start of my career. And this sign over there says onderzoek, which means in Dutch, research brings light. And I was exactly doing research in the building on the left, building 13, and that building was about battery testing and a number of other things. But my work there was to program a genetic algorithm using decarbonise Power Factory. And we were doing so for a European project along with other partners, and our contribution was this algorithm to place and size storage using this evolutionary method. So I started, and I would say that probably 3 or 4 months into the task, I discovered why everything was so slow. I took some measurements, and it turned out that setting the load and the generation into Dixieland took about 98% of the simulation time. So yeah, I was having simulations of 3 or 4 days, and I thought, yeah, this could be done probably in less than an hour or about. So I did a very small program proving the case, and I sent it to the support of Dixieland. And after quite some discussion, they acknowledged it was not possible to set the states faster through the API, which, by the way, I was programming in C++ and C# to make sure what I was doing the fastest possible exchange, but in the end, it was something having to do with the database and the design they had with the database. So, well, we dealt with it. We had very long simulation times, but we accepted them, finished the project. But I wasn't happy. As a data engineer, you always strive for perfection. And I went to the office of my boss, Theo, and I told Theo, I need to program my own power flow. We are using this commercial software, and their design is preventing me to go home in time. So I want to go home in time instead of being here waiting for the simulations. So he very wisely said, you know, doing a power flow algorithm is something really, really, really hard. And that's why we buy the algorithms from these companies. So I don't want you to spend your time on that. So because I'm very stubborn, I told him, okay, maybe you don't want it, but I still need it. So I'm going to do it in my spare time. So let's reach to an agreement. So in the end, I started something in C++, which is also in GitHub. It's called F-Potential. It is a very early work. It's not efficient at all, but it was something that I started exactly because I needed some insight inside the algorithm. I needed to remove all the waste that this 95%, 98% of waiting time was causing in my workflow. And I was told something. In those meetings with the management and me proposing this power flow, one of the managers told me that the power flow was a commodity. You know, it's like wheat. It doesn't matter one or the other. Both, all of them do the same. So what is the value if you do it? Well, the value is this. So these are 3 stages from the martial arts learning process. And those are Ha, the stage in which you copy and learn the traditional techniques, heuristics, and proverbs, much like Daniel San. At the beginning, he didn't know why he was doing all those exercises, but he just did it because he was copying and learning the traditional techniques. After some time, you transition to the Shu. You break apart and start innovating and discarding or modifying the traditional shapes. And then there's when Daniel San beats his opponent with such a spectacular kick. And after some time in Shu, you move on to Ri, where you completely move away from forms and open the door to creative technique and to come to a place where we act according to our heart or mind's desire without hindrance and without overstepping the law. And then you become Mr. Yeti. And that is the value of reinventing the wheel. So why do you learn martial arts? Why don't you hire just someone with martial arts expertise? Well, that's the same thing why I started a power flow algorithm. Because I needed to be able to innovate without hindrance and without overstepping the laws. So the question is not rather of why reinventing the wheel, so what if we don't? In my opinion, if we don't reinvent the wheel, we are perpetually in a state of Ha. At the beginning, you can only copy, you cannot see beyond the wall that is imposed. For instance, I couldn't see why I was not able to change P and Q in nanoseconds instead of several seconds. For instance, we see this very clearly, here, at least in Europe, with chip manufacturing. In the 90s, Europe used to produce around 80% of the chips it consumed internally, mainly for the car industries and some other electronics. But now it is not the case, and the chip shortage has made that very evident. And now the European Union wants again to have chip factories, but yeah, now you have to go again through the stage of Hari and Shu because you destroyed all that. So my point is that having the source code, having all the expertise to go from 0 to X gives you the ability to innovate. And if you don't, you just have to find some hacky ways to do things. And that's not a good idea. So let's speak a bit about traditional electrical software design. this is the kind of thing that when we open a paper and we read it, we find sometimes the process of the algorithm, and it looks like this. There's some input file, then there is some pre-processing in which we calculate the admittance matrix or injection voltages or whatever other inputs for the process. Then we do the process of the paper, and often there is some output. Let it be a text output via the console or file or something like that. And now let's imagine that we open a second paper. Well, that looks like that as well. And well, so how do we couple both? So there has to be someone, and this someone has been me many, many times, trying to convert the output of one into the input of two. And the question is there a better way to do this? And I've come to the realization through, I believe I've rewritten the engine of GridCal, the tool that I'm going to show a bit later, 6 or 7 times. And I've done it to pass from this kind of process to this other kind of process. It looks far more complicated, but it makes it easier in the end, because this kind of process eliminates the waste. I'm trying to eliminate all the superfluous tasks. So the design of GridCal has some central piece called the numeric circuit. The numeric circuit is nothing else than matrices and vectors. So what it contains, what the numerical algorithms want to compute. But at the same time, I'm not showing the numerical circuit to the users. I'm showing them the user interface in a very simple fashion. And I would say familiar. But to be able to deal with that, we have to have something in between. We need to have something called the main circuit. And the main circuit is structures that are computationally flexible, but are not good for numerical computation. So for instance, if I want to delete one bus bar from the system, I should also delete the loads and generators attached to that bar or whatever other line that is attached to it, right? So doing that in matrix structures is really difficult. It imposes an overhead because you really need to look in many places, and it's hard. Instead, if you do it with objects, that operation is very simple. But at the same time, if I was to pass those objects to the numerical algorithms, then those numerical algorithms would be very slow. So we need to have this design. And then, of course, each of the calculations, source circuit, power flow, optimal power flow, and you name it, all of them are a separate object. It's like a sandbox where you have this numerical process, and the output of the numerical process is not a file, or it's not a text output on a console. The output is another object, and the object contains all the results pertinent. For instance, in power flow, you will have the voltage vector. And what is the advantage of that? So when I want to run short circuits, one of the inputs is the voltage from the power flow. And then should I have to check if the voltage matches in dimensions with the power flow? For sure not. I know it matches because by design I make it so. So I'm eliminating all waste. So what do I get from having something that looks so complicated? I get flexibility, and I get a lot of time saving. For instance, the design of GridCal today includes a command line and a graphical user interface. And the command line, well, it can be a command line and it can be a Python library, simple. It allows me to do whatever I want, and I hope to show you an example of this later. And the graphical user interface allows me to use it quite easily, and but more importantly, allows others that don't know about the internals to use it easily and adapt the software. This is a couple of screenshots of the program, and over the years I've been adding things like the sigma analysis, which is something quite new that I will show later. Continuation power flow, then parameter diagnosis, which is super useful because you get a grid and you don't know who made it or which errors it might have. So there are a lot of expert rules there to check the inputs. There's also a random grid generator, which if you are an academic, sometimes you need that. If you want to generate 5,000 node grid, you just click 5,000 and generate, and there you go. Stochastic power flow. I'm going to close soon. Stochastic power flow, then maps and the files inputs and many other windows that we do not see here. Yes, over the years, I've also evaluated the tool, and on the left, we do have the voltages, the voltage deviations for IEEE 118 with PSSC and power factor, which it agrees, but that one is a very easy to have the same values. And on the right, we have the grid of the Iberic Peninsula, that is Spain, Portugal, and a bit of France. And then also the difference with PSSC, and it's also around the precision of the algorithm. So from my perspective, I've validated this tool very many times because I try to use it at work, because it allows me to be very efficient at work. And well, just this slide is to show about some of our users, and I guess we could have more users in Australia, right? But mostly all the users are in Europe and the United States at the moment. Some of them are in Brazil. And at least in Spain, some universities are using GridCal for teaching, and I hope to extend it further because it's for free and it's kind of nice for students. They don't need to know many things to use it, but they can go as far as they want to inspect the algorithms. A bit of the roadmap is this is what I'm planning for 2022 and beyond, which is better optimization algorithms, more HPDC multi-terminal research, better visualization, try to take as much as possible from the data science community, and of course, better public relations like tutorials, videos. This talk, for instance, is a part of that. And at least for the Spanish-speaking countries, now in October, I'm going to give 4 tutorials explaining everything from the very simple modeling to very advanced modeling, like implementing machine learning inside an algorithm. And maybe if I'm successful, I could do it also in English, but let's start by that. And this is something I would like to see happen. So we've seen in other fields that it comes some job description that gets all the hype. For instance, the full stack engineer or the data scientist. Do we have something like that in power systems? So my point here is we should have it. We should have something that I would like to call the power systems transformation engineer, or maybe full stack electrical engineer, however you want to call it. And it's some person that knows a lot about realistic algorithms. And I have here this excellent book from 1990 by Rejaga and Arnold, that it does have realistic algorithms, and they also explain how they did their software. And that's, I think, the greatest value of this book, is that the authors were also their own software developers. Then we do have this one about clean architecture, because of course, as I said before, we need to program. Even if we deny it, at some point, we need to do some coding, because that's what the challenge demands. And well, since we do have to do some coding, let's do it properly. And I believe me, when you read this book, if you thought you knew how to program, you realize you don't, because there's so many things that can be improved, can be more efficient, more lean, and that's what you get by reading these computer sciences books, particularly this one. Then I think this engineer that we need needs to understand markets, not only traditional markets, but these probably new markets are going to happen in microgrids and the integration of microgrids and the wholesale grids and all that. And I have this book, Investment in Electricity Generation and Transmission by Antonio Conejo, which is, I think, very interesting, because when you open it, it does have all the formulation and it does have code. which in my opinion validates the formulation. When someone is brave enough to give you a code, it's because they are not afraid of you trying. And last, and I would say the most important of the four, is database design and relational theory. And this one is about information management. A huge part of why the processors are so time-consuming for the majority is because the data is not properly arranged. So we need to know the 3 or 4 relational data laws, which are called the normal forms. And I believe that someone that knows about all this, a little bit, is far better prepared to deal with all the changes that we are facing, on top, of course, of electrical engineering, the traditional one. So to sum up, reinventing the wheel enables innovation. How surely is the traditional process that we also had here in Europe through the guilds, and we should recover that. We should not expect people to know everything. We should also have some kind of apprenticeship in which people go through the process. At least I am not expecting commercial software to deliver. From the meetings I had with the manufacturers, they very clearly tell me that the design is not going to change soon. So at least I must program my own tools, and that is really showing for us, because we have started to develop our own tools here in Red Electrica, at least independent from the manufacturers. And the advances are really great by doing that. The decarbonization comes in hand with Teradata, artificial intelligence, and massive calculations. And I believe there is no way around that. So that's why we need people with really deep IT knowledge and more flexible and modular tools. And that's what the open source gives you. If you can open a tool and strip away what you don't want, that's the ultimate flexibility. And for me, GridCal has been the way in which I join all the above. Let's go to the demo. Any question up to here? Am I still in the call?
Yes, you are, Santiago. Yeah, no questions so far. Maybe we'll wait after the end of the presentation, and then if everyone has got any questions, so we will ask.
For sure. So
Thank you. Very, very interesting.
I'm going to show a bit the program, just to.
Yep, of course. Thank you.
To speak a bit about how I did things and how I think about the software and the improvements I can put in the software, and yeah, the advantages overall. So let's start very small. So this is how I add a bus, 2 buses, 1 line. Let's put some reactance to the line. There you go. Generator. Load, and then the load, let's say, right. Flow. You see, the first time it takes a little bit because it's compiling internally some things, but the second time is, yeah, almost immediate. And like this, you start writing and writing and creating the grid. And eventually you end up with something more complicated, but I'm going to do it by steps in this demo. So yeah, so last year I started, well, actually in 2019, but it took like a year to figure it out. I started investigating how to do AC and DC power flows at the same time. So there were several approaches. There were like simulate the AC, simulate the DC, couple, and then do it again all the time. And I thought that's not really efficient. If I have a huge grid, then it's going to be an issue probably. And then I found a thesis by a guy from Durham University. And more importantly, there was a piece of MATLAB code. He extended MATPower with this AC and DC formulation, which is really fantastic. So I called him and I say, hey, let's do a joint effort and try to improve your algorithm, make it even more efficient, and I will do that in GridCal. And that is what allowed me to introduce this device, which is the VSC device. And the formulation of this person had 91 submatrices in the Jacobian. When, if you remember from the courses, the typical Jacobian has only 4 submatrices. So there was a massive effort to make it faster, and that allows me to have this very simple grid in which, well, now it's compiling all the routines, but we have this VSC, and we can have a lot of control modes. For instance, this one is controlling the power in the DC side and the voltage at the AC side. And the power of the DC side is 0.2. So if you look, yeah, 0.2. That's all right. Here as well. And it's controlling also the voltage here, so it should be 1. There you go. And we can have all these controls, and probably, yeah, you see that I created all of them joint in pairs, but of course we could have separated ones like PDC or PAC, separated group and all that. And this has been massive advances for me because I learned a lot in the process. I couldn't find any article or any book that explained how to do this properly, except for this one guy and his code. And this is a really competitive algorithm now because it solves the AC and DC at once in the same Jacobian matrix. And I've also had some other collaborations like that in the past with, for instance, the holomorphic embedding power flow, which I'm going to show in a moment. And this is something of great value that allows me to have this open source tool. I can contact some academic and really, all in good faith, develop something together and really be at the state of the art with very little effort from both sides. Then the person in the academia can probably publish something related to this because we improved the algorithms. We also made them in an open source tool, which is probably something that is valuable if you are publishing. And you can easily check against other state-of-the-art algorithms that are implemented in the software. So let's see this IEEE 39. And this one is a grid that has time events because I've created some time events. For instance, here we have all the active power in the loads. So yeah, for instance, if I want to plot this 3, so this is what it looks like. It's a complete year. So I can do something. Let's run the OPF here. Hope it doesn't take too long. I'm going to group it weekly. And the server is going to be the CDC, which is the open source one. And let's run this one. It's making groups. And it's going to take a bit, but I hope I can show something in the meantime. And in the meantime, I'm going to run this Helm sigma analysis, which I bet you haven't heard of. So what does this do? The holomorphic embedding is something that, to my knowledge, was first published in 2012. And essentially, it is a power flow algorithm that is not recursive, meaning that it takes like a trajectory from the no load point to the full load point. Imagine you have the same grid that we have right now, but where all the loads and generation is 0. So you solve for the, of course, when you have that, the solution is obvious, right? It's whatever the voltage set points are. But the thing is that this method extends little by little using a Riemann series, like a convergent series, to express the voltage. And you express the voltage as a function of the loading. And if you do that, you do have some curves that take you from the no load to the full load without possible deviation. And if there's no solution, is because the power flow itself didn't have a solution. Derivating from that, we can calculate this sigma thing. So what is the sigma? The sigma is a measurement of the real and imaginary parts of the voltage of how far is a bus from the collapse. And the collapse is represented here approximately with the black curve. So, as I said to my coworkers, I want grids where all the balls are inside the curve. If there is a ball outside the curve, that's bad, because the grid is in collapse. So this gives me a very visual and simple representation of if the grid is stable or not. And this came also from a university collaboration, actually from the Barcelona University, the technical one. There was a guy researching this, and I happened to have, at the time, the only open source version of this that didn't really work very well. But this guy was incredibly smart, and he made it work. And then one day he just sent me an email, like, hey, I improved your formulation. Here you have it. So I was freaking out, and then we have been in discussions for several years doing other stuff since, and this was one of them. This awesome tool was also a fruit of spontaneous collaboration, I would say, and all because I have this open source software, and I'm very open to collaborate with people. So I saw that you saw that it was running the OPF in the background. So okay, we have the OPF here. So if I click and plot a line, sorry, I clicked the wrong button. Plot files. This is the loading of this particular branch in the OPF, right? Good. What if I want the OPF results back into the Newton-Raphson algorithms? So I just click here. And there you go. The Newton-Raphson is solving way faster. And there you go, done. And if I plot again, yeah, there you go. This is the difference between DC and AC. Oh no. And well, I've used this many times to explain the difference between the typical Plexos loading results and actually checking with power flows. So, well, this one is quite different, sometimes depending. Well, if the line is, because that one was quite loaded. But if we go to one that is less loaded, well, this is also quite different, to my surprise. Well, my point is that you can do all this here, and also you can go to the results and see the voltage model, voltage year. There you go. This is how it looks. And if you go there to the OPF and click on the generation power, and do the same. And this is how it looks. And you will agree with me that this looks effortless, right? Compared to all the hard work that doing this is at least I was accustomed to using commercial software. In our traditional workflow with commercial loops, this thing that I just did takes about 3 days. Of course, with many more nodes, however you want to see it, but certainly it's not clicking a button 2 times. So this is what allows me. So when I see that something in my process is not lean, I just said, yeah, let's remove it. What should I do to make it better? Because again, I want to go home at 5, not being there afterward just because I need to do some Excel number crunching, right? Okay, so, but you said, yeah, 39 nodes. I'm not convinced yet. Okay, so let's use the Texas grid. This one, by the way, is coming from the Texas Open Grid repository, and apparently this one is synthetic. But it, despite it being synthetic, it really looks like Texas. I'm going to show you. Well, here it tells me that there are a lot of nodes. Do you really want to show the schematic? Yeah, I want to. So, yeah. So this is it. This is Texas. Let's run a power flow here. Well, of course, there are no PF results, so it didn't take any. So this is Texas, and this is the power flow, and it's quite fast actually. Let's have a look. 0.0 seconds, quite okay, to the power of -7. And I also did extend this Texas grid with some random profiles I have around. And this is, there you go. So yeah, it is different for every node, but it looks like this. It's a complete year, you can imagine. But you see, since this grid is quite large, maybe I don't want to run the complete power flow because I'm in a hurry. So let's just use the linear analysis based on the PTDF. And this one takes really no time compared to the traditional power flow. There you go. So now if I go to any branch around, like this one, and again plot, this is it. This is the flow around the year. How long did it take? I don't know, 20 seconds, maybe less. So yeah, all these Greek letters are the linear approximations. And this one I've been developing this year for some other calculations we need to do here in the company. I wasn't really interested in these linear things because they are not so accurate. Let's run the complete power flow and see. But still, they are super useful because they give you a hint of what's going on in terms of flows, at least. And of course, you can also run the contingency. And this one is the net transfer capacity between areas and a number of things. And well, while this runs, let me show you something. I hope that I have it here. Open recent. No, I don't have it here. So let's have a look at something else. So from the literature, sometimes we need to do this net transfer capacity thing, right? And this one is based on the PTDF in the power transfer and distribution factors, which if we open here the linear analysis, is this, no, I need to do this one. There you go, linear analysis and branch flow sensitivity. So this is how sensitive each of the branches to the changes in injection in any of the passes. And if we plot it and wait for it, yeah, it looks like this. And this is actually very nice because none of them go beyond 1, which is theoretically correct, hopefully. It looks like this. So this is the sensitivity of all the branches calculated at once. And we usually use this for this net transfer capacity. But what if we also want some exotic stuff happening? Like, for instance, we have some HDVC's connection between Spain and France. And we have a very exotic control type called the AC emulation, which I haven't heard of in other places, but maybe it exists. And that is the HDVC looking at the angles and correcting the flow depending on the angles. So having that in mind, we want to do this one. So the optimal net transfer capacity. So what we did was to formulate, I'm just going to show the optimal function, to formulate the problem as an optimization thing. So we maximize the flow from area 1 to area 2. Sorry for the track. Anyway, we maximize the generation in area 1. We maximize the power shift, and we minimize the cost and the deviation from Kirchhoff the branch overloads, the HDVC overloads, the HDVC control deviations, and something we call the delta slacks. And my point showing you this, which, yeah, what does it mean to you to look at some code? Well, probably nothing, but my point is we did this work in about 2 weeks. In only 2 weeks, we developed something completely new because we already had all the pieces. If we go back to this, we already had so many green balls to extend, and we already had the numerical set with which we contrast. It only took 2 weeks to create a new green ball. And that is one of the main advantages of having the source code, that you can do anything, even if it is this very exotic HDVC control, even if it is something that no one else has ever done. But if you can formulate it and you can think about it, you can just do it. And let's see if this finished already. Well, no, 70%. Well, this is mostly my demonstration. I could show so many more things, but I think I can start asking questions, responding questions already if you want.
Thank you, Santiago, for the presentation. It's been very informative, and I found it very interesting. Very great job on that. So I'm so impressed.
Thank you.
If anyone has got any question, they can ask through meeting chat. So yeah, we've got a couple. So I'll go through them.
For sure.
So the first one, Chris is asking, how would you recommend people who are unfamiliar with open source projects start being involved?
That's an excellent question. I would say start by something that is simple to you. For instance, around 2013, some projects like GridCal arose, like PipeSA, Panda Power, GridCal, and some of them, all of them in Python because it was the flavor of the day. And we all copy this Mad Power because it is simple. So my advice is first, just go and see something that you can tackle and try to do something that is useful for your daily work. For instance, some people sometimes ask me stuff like this other guy the other day wanted to do some time series, something quite simple in my opinion, but he just wanted to do it. So he wrote me and say, hey, what is your advice? How do I start? And I pointed him to some directions. At least I'm quite open to reply to anyone wanting to do anything. Some other person from Canada once wrote me that he wanted transformer automation, very detailed, and we did it together. I'm also aware that some open source owners are not so open to discuss, but at least I am. And I think my biggest contribution is by me being open. And if someone really wants to tweak, for instance, the holomorphic embedding algorithm, like this other person the other day, I just tell them, this is how you should start. But if you just want to start by your own, I would recommend you something simple. And to me, the simplest thing there is in this kind of open source power systems things is Mad Power. Maybe there are others that are also simple and elegant, but at least that one is the most renowned one. And for sure, you can contribute with this one.
Thank you, Santiago. So I'll go to the next one. Puati is asking, can GridCal accept real-time data import from already created models for trending and rolling analysis?
Yes.
Basically, yeah, okay.
Not off the shelf, for sure, but that's something we did. One of the companies that was a functionality that we need. So a real-time simulation. Let's see. So you get a sampling, let's say every 10 seconds or something, and then run the power flow and check, run the power flow and check all the time. So it's actually quite easy. It's a for loop, and then running the power flow inside the for loop and assigning the injections. So that could be a very good starting point, because it's quite simple in principle.
Thank you, Santiago. Next one from Gemani, if I pronounce it correctly. Can we do modification on the code, for example, to include optimization method like genetic algorithm or PSO to solve any power system problems?
For sure, for sure. The license of the program is what is called GPL3. This means that you can do anything that you want as long as you share the code once you do it. That's the license in a nutshell.
That's the beauty of it, I guess.
Yeah, exactly.
Yeah. Next question. This is the last question I've got from Julius. Have you experienced any challenges getting acceptance of open source software at Red Electrica?
Of course.
Mm-hmm.
Of course. But you know what? You need to have a candy. So what is my candy for them? My candy is these lambda letters. These lambda letters for them, huge pain. If we look to my coworkers as customers, a pain they had was, yeah, we need to do these exchange calculations with France. France is so much advanced than us because they already had this calculation linear one. And we only had this TLTG activity from PSSC, which is also this one, but you know, it's not adapted to use it with time. The only thing it gives you is a text report, and it's really uncomfortable to work with it. So my candy to them was, yeah, I can solve it. I can implement this NTC calculation also with time series, and I can give it to you for free. So now you see them using GridCal. But at the beginning, of course, how am I sure the power flow is the same as PSSC? How am I sure this and that? That at least I was sure that it was all right from the previous validations, but they were not, because our sector is based so much in trust that introducing something else makes it so difficult for others to trust. But if the pain is bigger than the trust issue, they will overcome the trust issue. If you solve the
Is there any other people in your company that use GridCal, or is it only you?
At least in my department, for this thing, I'm starting to spread it. So, but it also happens that when I arrived like 2.5 years ago, I started changing things around, and we did, for instance, right now, all the programs that we use in planning come in a package, something like GridCal, but it's not GridCal. It's a package with a lot of small utilities to do things. And my ambition is to have, well, actually, we are building in a research and innovation thing, is something map-based. So you just draw things in a map, and you click and see the substation, and you click and run the power flow and all that. So, yeah, if you do that, people already recognize how things work. And for them, GridCal is just another utility from the package. And that really smooths things for the adoption. And again, looking at the survey, if you ask them, do you really care if it is open source? Of course, they didn't even think about it. They just wanted something to solve it. And if you even think it further, there is a lot of internal open source already made. There are hundreds of scripts using PSSC, and that for you is open source, even if you don't share it with external parties, but it's internal open source, and internally it does have the same effect. You need to trust the person giving you that script that what it's supposed to do is correct. So this is kind of the same, but with graphical interface.
Yeah. So the studies you can do in GridCal are steady state, right?
It's a steady state for the
or
time being.
does it have any feature to perform dynamic studies as well?
Not yet.
Or do you have any plan to extend it, if I rephrase it that way?
There is the plan, but I must admit that I lack the knowledge to start it easily. So it would take me quite a lot of time to start it. So
yeah, of course.
I would really appreciate to incorporate something. For instance, Julie's here in the call. I really looked at your code for the dynamic part. I'm trying to get some inspiration, but I failed. So yeah, in the end, it's just the time that you want to put into it. And of course, I would love if someone would come and tell me, hey, I want to do a dynamic tool, and I think it's easier if I do it inside GridCal. So that would be nice.
I guess Julius can comment on it if you want, Julius.
I'm sorry you didn't get any inspiration from it, Sandy. It probably wasn't very good.
Yeah.
But no, it'd be great to have the sort of dynamic components in GridCal. I think it'd be a fantastic addition to it. And one day, hopefully, we should collaborate.
Yeah, for sure. I'm open to that. Time permitting, but yes.
Yes, indeed.
Yes.
Thank you, Julius. I've got, maybe this is the last question from Puvati again. So hi, Santiago, hearing about your answer for question 1, what is the real world implication you think would better define GridCal? Like would make availability of PSA for free, or improving efficiency of existing solutions, or creating a PSA ecosystem of its own?
Yeah.
It's a very long question.
So the real, as I might rephrase it, would be, what is the real world impact of having something like GridCal, right?
Yeah.
I would say that if you want to know how PSSC PowerFlow works, the best open source shot at it is GridCal at the moment, because I've compared so closely. Probably there are other ones that can say the same, but at least there's some innovations that I made inside, and by reading numerical things. In the end, my point is I use this commercially, if you think about it. So I'm one of those customers that tools want to sell me stuff. So because I work with it and because I work in a DSL, all those things. But instead I use this. So maybe that's the impact. So in one of the universities here in Spain, they teach with this. And the teacher tells me exactly that, and tells that to the people there. If you want to see how a real life PowerFlow works, this is it. It's not an academic thing that when you program the PowerFlow or the OPF or any of the other routines, it might or might not work because you didn't take into consideration so many things. You can have a look here. The same as I looked into MatPower, which was the huge contribution of MatPower, in my opinion, is to teach people how to make a real life competitive algorithm. And I think I go a bit beyond what they did in MatPower, and that's also a bit my contribution. And thinking a bit outside of all this knowledge management thing, if I get fired tomorrow, let's say like that, I don't have to spend 80,000 euros in PSSC or Dixisland. I can have something that is almost equivalent for free.
Yep. Really interesting point.
Yeah.
Another question from Jay. Did you say that we have benchmarked this against other load flow packages? I think you've shown a graph with that, but yeah, how does the accuracy compare? So you can
better comment on it.
Yeah, you can show it again.
the thing is that well, you see that this is to the power of -7, and this is also to the power of -5. Probably this is where the tolerance is.
Yeah.
Numerically, you can go until to the power of -15, 14, and there's where the actual floating double precision float already starts oscillating. But around this, you're pretty confident this is the same solution. What is the disadvantage or difficulty in checking this? That the options, whatever they might be, you go to PSSC or Power Factory, there are 1,000 options. You go to GridCal, there are 1,000 options, and probably they are slightly different. So you need to make sure that those options actually mean the same for the numerical algorithm to make the comparison. But if you do, you do have a valid comparison. And that's also the point in all this, because you can have so many controls.
And depending on the algorithm, I think the results are a bit different considering truncation error and other errors contributing into it. Thanks, Santiago. I've got no more question. I think that was it. On behalf of the PES chapter in Australia, Santiago, I would like to thank you and thanks for your time for preparing this and also the presentation. And another point is that so the video has been recorded. We'll put it on the channel. So in our channel for PES. So I'll put the address in there. So let me copy our channel address. So we'll upload it in there. So if anyone has missed it, so can watch it.
Perfect. Yes.
Okay, it's thank you so much, Santiago. If you've got any other comments or anything, just please.
Well, just anyone having any comment or question or willing to take over this work, you're very welcome to do it and to contact. So
we will be in touch. Thank you, Santiago.
Thanks to you.
Have a good day.
Bye-bye. Have a
Cheers.
good day. Bye-bye. Bye-bye.
Bye. Thanks, everyone.
Thank you.
Bye.
Thanks, Ali. Cheers.
Thanks, Dean. Bye.